Hello everyone. In this video I want to show you a simple demo of linear regression in TensorFlow. And we are doing everything in Google Colabs, as you know. So here again I import the four libraries that I need: NumPy, Matplotlib, TensorFlow, and Pandas. And the data I have here is for cost of health insurance coming from this website. I got this insurance.csv file from them, and I have added it manually to this local files. So I can read it with Panda in, convert it to NumPy. It has four variables for prediction, which are age, gender, which is 1 for female, 0 for male, body mass index, the number of children, and whether it's a smoker or not, 1 for yes, 0 for no. And the prediction is about annual insurance charges. Okay, so when you read them in, the first 5 columns, as I said, are the training data, and the 6th column is the target values. So here, let's go ahead and bring them in. So you see they are read in, and you can see them under variables, right? If you look for X and Y, you see X is 1338, number of people, right? 5 columns, and Y is just 1 column, as you can see here. And then here we need to use the reshape method here. Okay, and I explained that in my Python videos, but basically this reshape of -1 and 1 means what? Means to add that dimension of 1 to it. If you see, when I bring it in, it's just 1 column, okay, and you just get 1338 and no second dimension. But when I do that reshape of -1 and 1, you see now you have this extra dimension of 1 here, okay, and you need that for the regression training. So here you can see that this is the first row of the training data. The person is 19 years old, and a female, and mass body index is 27.9, and no children, and she's a smoker. And the annual charge she's paying is $16,884. Okay, so I have 13.38 people and 5 columns of data for them. Okay, and again, the 6th column is the value that I need to predict. I need to make a model for that. So first thing is I have to apply the standardization to the data. So from scikit-learn, I bring the standard scalar, rename it, and this time, differently from the binary classification, I apply fit transform to both X and Y, and I do not split my data into test and train. So here I use all of my data for training and just build a model based on all of the data. If you want, you can break it down again to test and train. But here, all of the data I'm using is training data. So you see, I'm creating a scalar fit transform on X and a scalar transform on Y, on my training set and my targets, or my variables or features and the target, okay? And I use them differently. So because they have their own means and standard deviations. Okay, so I transform them, and now I create a neural network model. Here again, I have an input model with only weights and biases, and F is the number of features, which is 5 here, and I only have 1 dense layer afterwards with no activation function. Remember last time in binary classification we had sigma width. Here we don't, because this is no classification, this is regression. In regression we do not use an activation function, or we use the identity or linear function. Okay, so even if you don't say it, the default is what? The linear function. So if you don't provide a name, it knows it's a linear or identity function. Okay, so again, keep in mind for regression we don't need that. And it could be as simple as that. So here we're going to only have 5 weights and 1 bias to train our system and perform a simple linear regression. And then again, remember, we need to talk about the optimizer, the loss function, or anything like that. And the optimizer we use is not Adam, it's stochastic gradient descent. And the first number you pass to it is learning rate, the second number is momentum. And I have explained them in my machine learning videos. I explained these two things, but basically this one is how much you move in the negative current gradient direction. And this one is the amounts that you use from previous step and inherit that, okay? So when the loss function is kind of going on a plateau, but originally or before, previously it was moving, but now it is going on a flat surface, it stops moving. It's not moving anymore, but since previously it was moving, this number helps it keep going down a little bit and moving along the almost flat plateau. The loss function also we use is not cross entropy, it's the mean squared error, MSE. And so we apply those to the model compile, and now I'm ready to fit. But before fit, I want to show you an extra thing. And remember, in my previous videos, I said that this learning rate you can adjust. You don't need to stick to a fixed learning rate. Now, what are the best strategies for changing the learning rate? That's a separate discussion. But if you want to change the learning rate, you can do that by creating what we call a learning rate scheduler function. So you need to use tf.keras.callbacks.learningRateScheduler, and to this you need to pass the name of a function that you previously defined, and this function will tell you how much of learning rate you need to use. Okay? Yes? So when I use my fit model and I pass my training data X and Y and the epochs, I can also, from the callbacks, I use my scheduler, which I define using this scheduler function to update my learning rate. Okay, now how can you do that? Well, the function you define for scheduling of the learning rate, in general, it takes in two inputs, the epoch number and the current learning rate, and then it returns the new learning rate. So you can say, for instance, if the epoch is more than 50, so here you're going to go 100 epochs. You say if the epoch is more than 50, is bigger than 50, right, or less than 50, something like that, okay, if it's less than 50, then go ahead and use the current 1 to the negative 4. Else, go to the 10 to the negative 5. Okay, you can go with constant numbers for some epochs and constant for some other epochs, or you can adaptively change it. For instance, you can say if it's less than 50, instead of returning this, you can use this bottom line. You say, hey, return the current learning rate, which means basically not changing it. But if it's bigger than 50, then what? Return the current learning rate times an exponential of negative 0.1. What does it mean? It means exponentially decrease the learning rate with the power of negative 1. Okay? So this way, you're going to reduce the learning rate at exponential of negative 0.1 per epoch, basically. Okay, so it exponentially goes down, or you can have them at a fixed number. So you can use either these commented lines or these lines that are not commented. You can define your function any way you want per epoch. Okay, and again, the inputs are epoch and current learning rate. The return is the one that's going to be used in the next epoch. So you can create that function, pass it to the learning rate scheduler, and call it a scheduler, and pass it as a callback function when you want to train your network. Okay, so here we have brought the data in, and here we standardize the data and pre-process them. Here we create the network. Here we apply the scheduler function, and here we train the network. This is where your loss function starts at 1.58, and you see your learning rate is 10 to the negative 4, but look what happens. Once you pass epoch 50, you see right before 50, you're at 10 to the negative 4. Once you pass it, now you're dropping to 10 to the negative 5, and it keeps going down, and you see your loss is not changing much. Very, very slow. Now, if you want to see the plot of this loss function, Again, remember, you can use r.history.loss here, and you can plot that. And this is the plot of the loss function. So here is where it's plateaued. Okay, and it's not really changing much. So you can play with this function if you know what you're doing, and basically change the learning rate so your stochastic gradient method hopefully can go further down if it can. Okay, so this is the plot, and then if you want to see the model summary or the weights, again, use the same thing as last time. So click here, and there we go. These are the 5 weights for the 5 features, and this is the bias, and your network has 6 parameters that can all be trained. And you only have 1 dense layer, and that's all it is. Okay, so this is a simple regression, and now if you want to do the test, you can do that again, right? You can just form a vector here. You can form a vector that has 5 rows, right? So it is something like this X. It has 5 rows, and you can pass to it to the model.predict, and that should tell you, for instance, how much of insurance cost you would be dealing with, right? Here, I have added that part for you. Now here you have to be very careful that, let's say this is the new person that I have, okay? And again, if you want, you can break your data into test and train and use only a portion of it for train. But here, I used all of my data for training, and now I have a new person who is 25 years old. It's a male, 32 BMI, 2 children, and a smoker. And now, if I want to get the insurance cost for this person, first thing first, I have to transform the data of this person using the mean and the standard deviation of X. So I have to first scale it. So here you see I'm only using the fit method, not transform or anything. I use the fit method to my X data. So this X scaling data can contain the mean and the standard deviation of what? X. Then using that mean and standard deviation I learned using fit, I applied the transform method to what? To this new data XX to get the transform version of that. So this data will be different now when I have this XX. If you want, you can print it and see that, okay? And then, now that I have the transform version of my data, it is good to be passed to what? To the predict method. So I pass it to the model predict, and it gives me YY. Now, can I get this YY and use it right off the bat? No, because this YY is also scaled down, so I need to re-invert. I need to get rid of the scaling. Using what data? Using the mean and the standard deviation of the Y data. So here you see I bring my Y data, pass it to fit again, and get this Y standard data, which has an average of Y and a standard deviation of Y. And how do I invert it? There is this method called inverse transform. So to this YY that I got out of prediction, I applied the inverse transform with that mean and deviation, which basically means multiply this by a standard deviation of this guy and add the mean to it. And get what? Get this inverted version or the scaling undone version of YY. And now this is the correct number. Look here. So this is my original data. When I transform it before I pass it to my neural network, look at the data. It looks completely different. Now this guy is ready to be passed to the machine. To my neural network, it gives me a Y, but that Y, again, let me print it here for you. That Y is not the correct Y. Look at that Y. That Y is like 1.3, and you say, oh, really? How lucky you are, $1.3 per year for annual insurance. No. If you multiply it by standard deviation of the Y data and add the average to it, the real number is what? The real number is 29,000. You're looking at 29,000 $1,000. Okay, so I comment this out for you. You just saw it. But remember that you have to do a scaling for the new test X, and once you pass to the predict, you have to undo the scaling for Y so you get the correct number out of the regression. Okay, so it involves a little bit of steps here, but you should be able to do it. And remember, you do not use an activation function in the last layer. And remember that you can change your learning rate if you want using a scheduler. And typically you go with MSE, or a loss function appropriate for regression. And the optimizer of choice is typically SGD, but you can use other optimizers as well. So hopefully this video was useful to you on a simple linear regression. I'll see you in the future videos. Thank you.